Hi. All right, so let's go ahead and get started. So the first thing we're going to do is we're going to be talking about functions. So we're going to look at graphs, how graphs are created, how relations form between independent and dependent variables. We'll talk about how you use those in various ways, how you can show what they work. So let's go ahead and actually get started. All right. So let's start with an actual kind of real example. So keep in mind, as I give this example, I am simplifying the whole scenario to have a fascinating period of history here. So in 1618, Roman Catholics in Prague told people that Protestants could no longer build churches. Protestants protested. They eventually kind of stormed the government building. They had a big meeting with a bunch of the governors and other people of the government. Some of them they let go, feeling that they were actually working in good faith. Others they decided were misrepresenting the law and circumventing the law, and they hucked them out of the third story window. To throw someone out of a window is called defenestration. There's your vocab term. So the governors somehow survived the 21-meter fall down to the ground. Later on, Roman Catholics said it was divine intervention saving them. Protestants later claimed that they had just landed in a pile of horse manure. I leave it up to you guys to kind of research, make your own opinion on that. So an object, when undergoing free fall, or if they're hucked horizontally out of a window, will fall at about the same rate. So after about a second, they'll fall in about 4.5 meters. After 1.5 seconds, they'll fall in 11 meters. And after 2 seconds, they'll fall in about 19 meters. So we have some information as these people are falling. And this information is linked together. So this forms what's called a relation. So in mathematics, a relation is a set of inputs and the matching outputs that form that data. So it shows a relationship between different quantities or different data sets. Here we have the relation 1 second, 4.5 meters, 1.5 seconds, 11 meters, 2 seconds, 19 meters. So this actually forms our relation, something time elapsed and distance fallen. Now we have 4 ways in math of showing these types of relationships. We can show them with ordered pairs, we can create a mapping diagram, we can form a table, or we can actually graph it. So we're going to take a look at each of those for our specific example here. So first are ordered pairs. Ordered pairs always link the independent variable and then the dependent variable. And that's where it gets its name. It's ordered. So it has to be the same order for all the data, the X and then the Y. The H and then the K, whatever it might be, but it has to maintain that order. So we have our 1 second, 4.5 meters. We're going to create an ordered pair in parentheses. So we have 1 comma 4.5. We have our 1.5, 11, and our 2, 19. Always written out with commas separating out the data from input and output, and written in parentheses. So this is our ordered pairs. The second way that we can show it is through a mapping diagram. So a mapping diagram lists out all of the inputs, and then it lists out all the outputs separately, and then it connects them visually. So when we write these, I'll usually write it out as a column. So all of our inputs are our 1, our 1.5, and our 2. And it's always better to put these in order, in increasing order. So 1, 1.5, 2. I'll then write our outputs, which was our 4.5, our 11, and our 19. Put circles around them, and then you show the relation between each one using a directional arrow. So we have an arrow going from 1 to its matching output, 4.5, going from 1.5 to 11, and then going from 2 to 19. So this whole little diagram, our inputs, our outputs, and the arrows connecting them, is our mapping diagram. We can do it with a simple table. So the table is going to look very similar to our ordered pairs, just written out in a pretty format. And then you should, if it is available, have labels for what the table should represent. So we have time elapsed in seconds, we have distance fallen in meters, and you'll notice that as we go across, it's essentially just our ordered pairs again. So we have 1 matching with 4.5, 1.5 with 11, 2 with 19. So now I have my table written up with values. Finally, we can make a graph. My graph here is not very pretty as I was experimenting with creating graphs in slides and not actually succeeding very well at the moment. So we have a basic graph. We should be labeling the axes as to what they are. So the y-axis here should be distance fallen. x-axis should be time elapsed, and then we can draw our points for the graph. So again, those are our 4 ways that we can show our relations. We have our ordered pairs, mapping diagrams, table with values, and then graphing. So that's it. So now, when we talk about the data itself, you have all the input stuff is what we call the domain. So that's usually all the x values, all the independent variable, however you want to call it. The range is all of the y values. It's all those things that were with the y. So here, with our example of our points 1, 4.5, 1.5, 11, 2, and 19, our domain is simply 1, 1.5, and 2. It's all of our x values. It's all the independent variables. Our range is simply 4.5, 11, 19. So it's our y values is our range. Our x values are the domain. That's our basics of domain and range. All right, so let's try one out. So we have some kind of relation that's already given to us, and it is a ordered pairs. So we have 1, 2, 4, 5, 8, 19, 9, 7, and 10, 22. So this forms our relation at first. So we're going to show it all 4 ways. One of them is already there. Then we'll identify the domain, we'll identify the range. So in this case, 1, 2, 4, 5, 8, 19, 9, 7, 10, 22, let's actually start writing it out. So let's try their new board here. Okay, so our first is ordered pairs. Ordered pairs, that was easy enough. It was actually already given to us. So let's write it out. So we have our ordered pairs of 1, 2, 4, 5, 8, 19, 9, 7, and 10, 22. So there's our ordered pairs. Okay. We can do a mapping diagram. So again, with a mapping diagram, I'm going to list out the x's first. So we have 1, ooh, red, there we go. 4, I'm going to try to put them in order. 8, 9, and 10. We have our outputs, which I'm going to try putting in order. So we have 2, 5, 7, 19, and 22. Wow, this is awful. I'm really bad at writing with the mouse. So we have our inputs and we have our outputs. So now to finish the mapping diagram, we're actually going to add arrows going from each one. So our 1 goes to the 2. We have 4 goes to 5. 8 goes to 19. We have 9 going to 7. And we have 10 going to 22. So there's my mapping. Okay, our third way was simply doing it as a labeled table. Okay, so that one's pretty easy. It's very similar to our ordered pairs. Now, we don't really have much in the way of labels, so we have, oops. Where did they go? I think I somehow blew it up. There we go. All right, so on this then, we have a couple different options to try using it. So when we draw it out as a table, we can actually go ahead and write it out. And here we don't have any actual labels for it. So there's no point in doing a label. We can't do it. So we have X and Y. So we have 1, 4, 8, 19, 9, and 10. Now I'm going to write out the independents in order, but the dependents need to match them based on their ordered pairs. So we have 1, 2, we have 4, 5, we have 8, 19, 9, 7, and 10, 22. So there's my table. Final, wow, that really doesn't like it keeping the formatting, does it? All right, so maybe not use the software for tables. Finally, we can do a quick graph. Looks like our x's are going 1 through 10. Y is going 2 through 22, so maybe by twos. So we have 1, 2, 4, 5, 8, 19, and 9, 7, 10, 22. There's my badly done graph on this. Okay, so we've shown all 4 ways: ordered pairs, mapping diagram, table, and graph. Okay, so let's go back. So functions are a very specific type of mapping that has one main rule. So a function is simply a mapping or a relation in which each independent variable, each input, can only have one output, exactly one output. So let's try to look at some examples because that'll make a little more sense. We have 4, -1, 8, 6, 1, -1, 4, 1. Well, we have the input 4, and 4 is going to -1, but 4 is also going to 1. So that's one input, 4, with 2 different outputs. So this is not a function. All right, so let's try a mapping diagram then. So we have our inputs and we have our outputs. -3 is going to -2. 0 is going to 7. 4 is going to 1. Each input is going to one exact output. So this is a function. That one succeeds. Okay, we have 2, 3, 4, 6, -3, -1, 3, 6 as our relation. It's in a mapping. 2 is going to -3, but 3 is going to -1 and 3. So this one input has more than one output. This is not a function. No good. Here we have -7, 14, 9, -7, 14, 7, 7, 14. So notice that each input is different. Each input has only one output. It is okay that both -7 goes to 14 and 7 goes to 14. You can have different inputs give the same output. That's fine. The same input can't have different outputs. So just be careful with that. So this one is a function. It works. Each of our inputs goes to one single output. So we're good. Okay, so the vertical line test is a little bit different. So it's an easy visual way of telling if something is a function. So if we have a graph and we draw a straight up and down line, that straight up and down line can only intersect it a maximum of one time. So it's okay if it doesn't touch the graph. It's okay if it touches it once. If it touches the graph twice, it's no good. So let's look at a couple examples. All right, so let's say we have one of our good old friends, a linear equation of some kind. Okay, so this is some y equals mx plus b. It's a straight line going up and across. And now we can start drawing vertical lines. So if I draw a vertical line anywhere I want, it's only going to touch the graph one time. So this is a function. We're good. How about a parabola from like midpoint of algebra 1? So if I have a badly drawn parabola here and I draw a vertical line, anywhere I draw that vertical line only hits it once. So we're good. This is a function. Okay, how about if we look at an ellipse? Some kind. Okay, so here, if I draw vertical lines over here, it doesn't touch at all. That's fine. I draw a vertical line here, it hits the graph twice. This is not a function. No good. It intersected more than once. Okay, how about a sideways parabola? That one actually came out a little bit better. Okay, same thing. I draw a vertical line, doesn't touch, that's fine. I draw a vertical line here, touches more than once. No good, it is not a function. So that's all the vertical line tests is. It's an easy way of testing if a graph is a function or not. Okay, so let's go back. Now, function notation is kind of a special way of writing our y equals. So we have function notation is going to be a letter saying that it's a function. It's going to tell you what the variable is, and then it'll give you what the relationship is. So this would be read f as a function of x equals 3x plus 5. Or you can just say f of x equals 3x plus 5, or g of x, or h of x, or k of x, whatever the letter might be. It doesn't much matter. It's just a way of naming it. So x is going to be the input. It's our independent variable. F of x is the output. And functionally, when you look back at Algebra 1, this is pretty much the same thing as y. It works the same way. So y equals 3x plus 5, f of x equals 3x plus 5 are almost interchangeable. So we're going to be able to go back and forth and just think of it like y as we work. So again, f, or whatever letters out in the front, tells us the name of the function. In the parentheses tells us what the variable is, and then it tells us what is done to that variable by the function. So this means that we can actually plug in inputs for them. So if we have something like f of x equals negative 2x plus 5, we can actually plug in various inputs. So -3 or 0 or 1/4 in this case. So when we write it out, we have our f of x equals -2x plus 5, and we can replace the x with that input. So if we're doing f of -3, if we're plugging in -3, I actually write f of -3 equals -2, and then instead of the x, I put -3 in parentheses plus 5. I can now simplify that using our order of operations and get 11. So -3 times -2 is 6, plus 5 is 11. I can plug in a 0. So f of 0 would be -2 times 0 plus 5. That's just 5. I can plug in any value I want. So 1/4. F of 1/4 is -2 times 1/4 plus 5, which is 4.5. So again, inputs are just direct substitution into the function notation. All right, so let's kind of verbally go over these. So we have f of x equals -4x plus 1. And they want to know what the output is. So that's kind of like what the y value is for any given input. So we have -2. So if I plug in a -2, I'd write f of -2 equals -4 times -2 plus 1. And that would give me what, -7? So -4, no, 9. -4 times -2 is 8, plus 1 is 9. If I plug in a 0 for it, I'd get f of 0 is equal to -4 times 0 plus 1. That's just a 1. If I were to plug in a 5, that'd give me -20 plus 1 is -19. So you're just substituting in the value into the notation. Okay, set notation is kind of the newer, weirder thing when we start looking at these. So set notation is a way of writing out things like domain or range. It's talking about all the numbers that we're working with. So our basic way of writing this then is you're going to have any sets in these curly brackets. That's telling you that it's talking about a set or a grouping of data. You're going to say what the variable that people are using is, so x. You'll often see either a colon here, so the 2 dots, or a vertical line. It basically means such that. And then it'll talk about any rules that apply. And they'll separate the rules by commas. Now here, this looks really scary or intimidating. It just means that x has to be an element. That's what that backwards kind of E looking thing is, of the real numbers. For the most part, we're not going to bother with this for most of our class. Most of our class, we're going to be talking about the real numbers. So it's only if something else happens, they're not going to mention it. And then, for example, another rule could be that x has to be bigger than 5. So this would be the set of all x such that x is an element of the real numbers and x is greater than 5. Let's say that we want to write a set where x just can't be 0. It could be anything else. Then again, we would use our curly brackets, and we could simply say that x, it's the set of all x such that x is not equal to 0. And that would be it. That would show our set using just the set notation. Okay, so interval notation, you guys have done some of this before. I don't know how much of it. You've definitely done inequalities before. I don't know how much work you guys did with interval notation itself. So let's look at a couple examples. So remember, when we wrote inequalities or graphed them, we could have something like x is greater than a. When you went and you graphed it, you would use either parentheses to say it couldn't touch, or maybe some of you learned it with open or closed circles. It's like an open circle saying you can't touch, and then you would draw the arrow. And that's fine. I don't really care which way you use it, open circles or the parentheses. I did it with open circles. It doesn't much matter which way. But it does help with the notation. So when we write an interval notation rather than an inequality, what we're doing is we're reading the graph going from left to right. So as we come across going from left to right, we're starting at A, but we can't actually touch it. So we're going to use a parenthesis to say that we can't actually touch it. And then it goes on forever. So we go all the way to infinity. And since we can't actually get to infinity, we're going to use a parenthesis again. So parentheses mean we can't touch it. Brackets would mean that we can touch it. And we're going to write it out as almost like an ordered pair. So the left to right as we go. If instead we were dealing with x is less than some value, right, that would be our graph going off to the left. Well, when we read this from left to right, we're starting way over there at negative infinity. So it's negative infinity, and we come all the way up to whatever our value is of a, and then we would have our parentheses again, because we can't actually touch a. All right, kind of the flip side of that is, let's say this example, we're going all the way to negative infinity, but we can touch a, we're good. So this would be an example of like x is less than or equal to a value. X is less than or equal to 2 or 8 or negative 15. It doesn't much matter. So again, as we read it from left to right, we're going all the way to the left as far as we want. So we're starting at negative infinity over there with the parentheses because we can't be at infinity. And then we're coming all the way up to a, and we can be a. We have an equality. So we're going to mark it with a bracket. We could be going between two values. So this would be your compound inequality from before. So a is less than x is less than b. And in interval notation, then we're going from a to b. It's the stuff in between. But we can't actually be each one. So we would just mark it with our parentheses. We could be going between them and having them actually touch, in which case we could use the brackets. We could have it be a little bit of a mix. So we could have less than or equal to b, but greater than or equal to a. So that's between a and b, and we can touch the a, but not the b. So that'd be a bracket at a going all the way to b. Now this is a little bit confusing when you first look. Keep this as like a little reference chart to help you out. So let's look at a couple examples here. I'm using the open closed circles instead of the parentheses brackets on it. Like I said, either way is fine. So here we're at 2, but we can't actually touch it, and then we're going on forever. Here we're at 3 and we are touching it. It's our closed circle. At 4, touching it, closed circle. So it's anything in between and including them. Here we're starting at -1, going all the way down to negative infinity, and we are including it. Here we have an open circle at 7 and going up to 15. So we're not including the 7. We can touch the 15. So let's kind of look at what our domains would be for each of these then. So our first example was going from 2 all the way up to infinity. So as we go left to right, we have 2. It didn't include it, so we have our parentheses. And we went all the way up forever to infinity. And infinity always uses parentheses. As an interval, that was simply x is greater than 2. And the nice thing with interval notation like this and inequalities is the set notation is usually just you reusing those inequalities in it. So it's the set of all x such that x was greater than 2. Our second example, we were going between 3 and 4. Going between 3 and 4, and we were able to include it, so it worked. So we have 3 and 4. We start on the left at 3, went to the right at 4, and we use brackets to show that we can actually connect to them. So our interval notation, or our inequality notation, would be 3 is less than or equal to x, which is less than or equal to 4. X is in between them. It could be equal to both. And there's our set notation. It's the set of all x such that, and then we can just use our interval again. Inequality. I keep saying the wrong one. Number 3, we are at -1 up here, and then it goes all the way down to negative infinity. So again, we always write the intervals from left to right. So we're going from negative infinity up to -1, and we were able to be -1, so we use a bracket. Our inequality notation then is just x is less than or equal to -1. We have our set. Our final example was going from 7 to 15. With 7 being an open circle, meaning we can't touch it. 15, we can. So we have open circle at 7. That's as far left as we can go. Going to 15 with a bracket because we can touch it. So that 7 is less than x is less than or equal to 15. And we have the set of all x such that 7 is less than x is less than or equal to 15. So there's our examples. All right. Range. So range is the same thing as domain. It's just going to be for the outputs. It's the y's. We can still do it however we want. We can still use set notation or interval notation or inequalities or whatever might be appropriate. So let's go ahead and take a look at, I think we're almost done here. Take a look at our domain and range of a parabola from way back when. All right. We have f of x equals x minus 2 squared plus 3. Now, if you remember what that looked like, good. If you didn't, that's okay. We're going to kind of sketch it. So we have x minus 2 squared plus 3. So we have x minus 2 squared plus 3. So this is a basic parabola. So thinking way back when, and that was like horribly not straight. I'll actually do it pretty. All right. So we have our axes. The basic parabola, when you guys talked about parent graphs way back when, our basic parabola basically looked like a U and it did this. All right. And then we could apply transformations. We're going to talk and review transformations next week. So it's okay if you don't remember. This is a parabola that's been moved right 2 units and up 3. So our actual graph here would be right 2 units, up 3 units. So it'd be a parabola like that. That is awful. Okay. Even by my standards, that was awful. All right, so it's been moved right 2 and up 3. So we have a parabola up there. So now let's try to figure out, we know that little vertex right there is 2, 3, what our domain and range would be. So as a parabola, it goes on forever left and right. So our domain then can go all the way to negative infinity, all the way to positive infinity. We can include anything. Our range are all the y values. So notice that we have no y values down here, and then we start at 3 and it gets bigger. So our range is going to be from 3 all the way up to infinity as far as we want to go. So let's kind of take a look then at what we would get for this. So if we take the domain and range of f of x equals x minus 2 squared plus 3, again, it's a parabola. It's been shifted 2 units right, 3 units up. It goes on forever, left and right. So the domain is negative infinity to infinity. That would be using interval notation. If we wanted to write it as an inequality, it'd be negative infinity is less than x is less than infinity. If we wanted to write it as a set notation, we could just say the domain is the set of all x such that, put our inequality. Or since it's just everything, we could just say x is an element of the real numbers. It's any real number we want. Now the y values, our range, we start at 3 and then it goes up forever. So just like we go left to right, we're going to go bottom to top with the range. So the range, we start at 3 and it can include it. So as our interval notation, we can have 3 with brackets going to infinity. We could have 3 is less than or equal to y is less than infinity, or if you want to think of it, that's just y is greater than or equal to 3. That's also acceptable. You don't have to write it as the compound if you don't need it. And then we get the set of all y such that, and then we can write our inequality notation again. All right, so the homework is posted already online. You can see it, do the best you can. It's okay if you get a little bit stuck on the word problems. I will answer questions, kind of go over them with you. I'll especially be pretty forgiving here at the beginning as people kind of look and try to remember how to do this stuff. So try to get the easy ones down, show all the work. When you get things wrong, that's okay. Come back, make your corrections, earn some of those points back. All right.